This set of videos will cover data screening in R. So I have several data screening videos for SPSS. This half will cover R. So we're going to start with accuracy, and I'm going to break it down into little mini videos so they're not so long. So this section only covers accuracy and how to fix accuracy in sort of 3 different ways. Okay. All right, so starting with the PowerPoint here. Why data screening? Well, if you've got all of this data, what do you do now? Just a word of warning that while I use the Andy Field book in R for my course, the data screening is actually more biased towards Tabachnik and Fidel's chapters on data screening, um, which are fantastic. They're a great reference, and so if you want to cite any of this information, most of that is from their book. But very technical and a little sleep inducing if you don't like stats books like I do. So the rules I'm going to use are similar to the field information, but if you want to cite something, go with Tabachnik and Fidel. I think their newest edition of the multivariate statistics books came out in 2014. All right. So why is data screening so important? Well, it's important to understand the data that you have and to make sure that the results that you present are appropriate. So we're going to check for errors in the data, which is the accuracy component in this video, and the next video covers missing data, and then outliers and assumptions. But you should always check for any errors in the data, items you need to reverse score, that sort of thing. Outliers, even if you don't delete them, missing data. And then assumptions, it really depends on the type of test you're running. So I'll say this again later, but these sets of videos are really for any type of analysis, with the reminder that some types of analyses use these assumptions, some don't. And every analysis has its own diagnostic plots. So this is a overview that you could screen any type of data, which gives you a little bit more flexibility than having to know, okay, for LM functions, I'm going to do this. For AOV, I'm going to do that. And this is sort of a big overview of you can do anything. And so I jokingly call this my big important rule. But when we're talking about hypothesis testing, so testing if the research question has been supported or not, really we're going to set an alpha level. And this is very confusing to students because we tend to talk about it as the p-value, so p less than 0.05. But really what we're setting is our alpha, our acceptable level of type 1 error at 5%. And we use that p less than 0.05 as a criterion. So if it's less than 0.05, we say it's statistically significant. So it's important to understand that we set an alpha level, and then when we run the statistics, we find a p-value. So p-values are specific to that particular test. Whereas when we say we want less than p less 0.05, we're talking about type 1 error rates. And that's hypothesis testing. But this is actually data screening. So for data screening, we want to use a stricter criterion, and this is really where it deviates from the field book. And because I've always learned that we want the data to be very screwy, so very, very bad before we start to change things. So we're going to use 001 to say that things are bad. And to show a little bit of my age, we jokingly called this rule the New Kids on the Block rule. Because you don't want things to be O, so the right stuff song. But we don't want things to be less than 001, so 000, because SPSS doesn't do more than 3 decimals. It used to be, if you see 000, remember it's bad 90s pop. So we want things to be greater than 001. So p less than 0.001 means that the scores are very screwy, and that's when we might start to fix them. Okay. So here's the list we're going to check in order. We're going to go through accuracy, missing data, outliers, and then the assumptions. So additivity, normality, linearity, homogeneity, and homoscedasticity are kind of the big ones. And I have a video for each one of these types just to help break it down so it's not so long. So why should you do it in order? So a really big component of this is doing these steps in the same order every single time. Once you get to the it depends section, it's not such a big deal, but the first 4 bullets, it really is important you go in that order. Let's say if you fix something, an accuracy a typo, or you reverse score, and then you replace missing data, take out outliers, basically everything that comes after that is affected. So if you find a typo halfway through your analysis, you do have to start over because that typo might become missing data, or it might make a person an outlier where they weren't before. So doing this in order is very important because it changes the steps after it. So this example data set is modeled after a paper from Stefan Schulenberg's lab at the University of Mississippi. He studies logotherapy. And I work with their lab a lot, so I have a lot of examples from their lab. What they did was they collected data to assess resiliency in a teenage sample, so a younger adult sample after a natural disaster. So this research paper is going to get published very soon, so hopefully by the time you watch this video, it's been published. Over looking at their meaning in life scores, the resiliency, and it was after either Katrina or the oil spill or both, I can't remember. So it has this RS14 scale. It measures resiliency as well as some other demographic variables. So this is an example modeled after their data, but it's not their real data, because otherwise I would get in trouble. So let's import that data set to get started. And I'm going to start by calling it master data set. Okay, oops, wrong click. This one. Okay, so let me set my working directory to where I have this data set squirreled away here. I think it's under notes. Okay. All right, so I would copy that and hang on to it again later. But now under files, I should be able to see that data set. So I'm going to import that chapter 5 data set called master data. Okay. Chapter 5 data screen.csv header equals true. Okay. So now I have this data set, and it's got gender, age, socioeconomic status, what grade they were, how many absences the natural disaster caused them to have from school, and then the 14 questions on the resiliency scale, which is by, I'm going to butcher this, Wagnall. And so what we want to do is start screening that data set. So we're going to, in this example, check for typos and other issues with the data. Now, typos are going to be less common if you're using software that collects data for you, like SurveyMonkey or Qualtrics or ePrime or Quizlet or any of these programs that allow you to sort of program in what you're wanting to get. And this is not paper forms anymore. This is a good time to reverse code items that you need to reverse code, especially if you're going to do like a factor analysis, because that will screw with your factor analysis, or you're creating subtotal scores, that sort of thing. Okay. We're going to start with the table function, or you could do the summary function to start. But this is really good for checking data that's categorical. So across these couple of videos, because I'm going to record them all at once, this is the normal Sunday evening in my household recording videos, I'm going to make this kind of Word doc here that talks about the paths I would tell you to take. So the first thing you want to start with is checking for accuracy. But there's sort of 3 different ways that we can do this. So let's start by talking about how do I fix categorical items. And so with categorical items, what you really want to do is use either the table or summary function. I think table is probably a little easier. And what you're doing is checking for coding or incorrect labels, etc. And so if you have a categorical item that needs a label, you can use the factor function to label them. Oop, I didn't want to save that. Cancel. Okay, there we go. So let's start by checking out our 2 categorical items. So my master data set has sex and grade sex and SES are categorical items. Okay, so let's look at a table of those. Okay. And so the first one you see here is that I have 1, 2, 3. And this data set is supposed to be male, female, and nothing else. So that 3 is an incorrect problem. So I can use the factor function to drop categories that I don't want anymore. And you can do this with a variable that's already factored as well. So let's go ahead and do that and fix this variable because it's problematic. Okay. So the first thing I'm going to do, before I even start actually, is set myself a data set called no typos. And so now I should actually use the no typos data set. And why would I do that? Well, I'm going to do that here because let's say I make a mistake and I type something wrong and accidentally wipe out a variable. So this happens a lot when you're first learning R and you type in the wrong thing in the levels command or something. And if you do that, it might wipe the variable out completely. And you might get 3 steps later and realize, why is this all NA? What you can do is then back up to this point and just reset the data set at that step. So with each one that I'm going to go through here, accuracy, missing, and outliers, is I'm going to stop and sort of create it in a new little data set. And what that does is it allows me to compare data sets as I go. So I can look at the number of observations and the number of variables if I'm starting to drop columns or rows, but it also allows me to back up to just the previous step if I make a mistake. That does take up more RAM, like working memory on your computer, but generally these R can handle that kind of thing unless you're on an older computer. If you have very, very huge data sets, it might be worth the trouble of like exporting the file and then re-importing it so you're not creating very large data sets multiple times. But I find when you're learning, this helps so you don't have to go back and rerun things a bunch of times. Here's the other reason. Let's say you decide to run your analysis with and without outliers. You could do some little subsets or some little select commands, but if you have a data set that's with outliers and without outliers, it makes it really easy because you can cut and paste your code and just change the data set name as part of the analysis. So there are pros and cons to this approach. Mostly the con is the memory space. It does tend to take up a lot of space. But like I said, you can export the data and then import it later, like this is the no typos one. So however you want to do it, but I'm going to go with this route. So let me fix this column. So I'm going to fix it in my no typos one because that's the point. There are no typos in this. So we're going to use the factor command. So factor requires you type the data set name, the levels. Okay. Whatever you put here has to be in the data set. So if these already have character labels, they have to match. So if my variable names were already male and female and other, and I just wanted to drop the other, I would type male and female here. Okay, so the levels here have to match, and they have to be in the same order as the data set. So I'm going to do 1, 2 because that's what I have and I want to keep. And then the labels command says, what do you want to label those things? And this is men, women. You can do 2, 1 to put them in a reverse order. So this will also let you reorder the labels. One issue with that is, like, let's say you're making a picture of the data, and that will order the data for you, but R will do most of the output in alphabetical order anyway. So there's a different re-leveling command that makes a different group, the comparison group. So when we get into ANOVAs, we'll talk about that more. Okay. I did not like that. Oh, I told it to factor the whole data set. Oops. Okay, sorry. The first piece of factor is that you need to put in the column name. Gracious. All right, let's try that again. So this time now, I should have it as a factor variable. So you see that here. If I run line 6 again, now I see that my data set's just men and women. So I have cleared out the problem code from here. Okay, so that's one categorical item. Let's look at the other one. Sorry, so it's SES here. There we go. All right, so it's 1, 2, 3, and that's correct. It's supposed to be low, medium, and high. So I'm just going to factor that variable so I know it's a factor command. I know it's a factored variable and not a continuous variable. Okay, so the column name, the levels. So since the levels are 1, 2, 3, I need to have 3 of them there, or it'll drop the 3. And the labels, let's go low, average, and high. All right, let's run that. We'll run line 11 again, and now they're correctly labeled. Okay, so that's sort of step 1. Let's fix our categorical variables. I think I did this. Okay. All right, so now let's work on the continuous variables. So now that we've done the categorical variables, we're going to work here. Let me make this just a touch bigger. There we go. On the continuous items. And there's sort of 2 paths with that. We can fix them one at a time or multiple columns at a time. All right. So with continuous items, the easiest way to start is this summary function. So I'm going to do summary of my no typos data set. And so that's true of either one. So I'm going to say start with the summary function. Remembering that Word autocorrects, and it's not, these are all going to be lowercase. All right, so let's do a summary of no typos here. And there's a lot of stuff going on here, but mostly what I want to look for, this doesn't always copy the best into Word. Let's try it here. There we go. So it doesn't always line up appropriately, but what I want to look for here, so I got my age, is mostly the min and the max rows. So the minimum and then my maximum down here. And since that line doesn't line up super well, I just have to kind of guess. But let's talk about doing these one at a time. So the age here has a maximum of 35. Oh, no, wait. The age is the maximum here of 18. So that's appropriate for this data set. The grade here is a maximum of 35, and the absences is a maximum of 35. That's probably not correct, because grade should only go up to 12. My resiliency scale here ranges from 1 to 7. So I'm doing good because I got 1s up here, 7s down here. But then I made some bad data in here to show you kind of how you might fix all of these scales at once. But I clearly have some out of range scores here. And these are either typos or some issues with the way it imported from the software or whatever. They're fake typos, so I can make this work. The other thing your dataset has is NAs. And so we'll get to those in the next video, but this is also a good way to look at the NAs. So let's talk about how to fix them one at a time. Back here. All right, so we're going to check the high and low values for minimum and maximums. And there are some high values of 35, and so there are things that are clearly out of range. And just a warning that if this is the data that you collected, you're going to know what out of range means. And so for this scale, it's 1 to 7. So what we want to do is, if you have some way to go back and know what those points are, go back and fix those actual points. So if you can look up the participant number and go, oh crap, that's supposed to be 5, fix that, because then you don't lose the data. But if you don't know what the data should be, delete just that data point. So we're not deleting the entire person, just that one incorrect data point. So let me show you what I mean by that. So I'm going to view this data set real quick here. And our absences data has a 35. And since the top of the data is 7, that's clearly a typo. If I knew what that person was, I would fix that. So it's either a 3 or a 5 maybe. Since I don't know what that person is because I made this data up, what I want to do instead is just delete the 35. So that whole person gets to stay, and it's just the 35 that's got to go. Okay, so don't delete the whole row. Just delete the one bad data point. And that was more important when I taught this in SPSS, but again, we're not going to like subset them out. We're just going to delete that point. So we're going to set, we're going to do one at a time here. I think this is where I start doing multiple columns at a time. And there's sort of 2 ways to do this, but one of them we figured out in class does not always work. So I'm going to show you the way that should always work, if I can remember it off the top of my head here. So the first thing you want to do for one column at a time is let's just check real quick and make sure that that's really what we want to do. So I'm going to look up my no typos, if I can spell it correctly. And I just did a table, and clearly that 35 is out of range. And so what you want to do is first find the problem child. Okay. So, oh, I am going through it one at a time here. Okay. So what you have to do is find the values. So we're going to use the logical operators. And so logical operators are where you're setting up sort of a true-false statement to see if something matches what you're expecting or not. And we're also going to use the subsetting or calling rules for matrix format. And so remember that matrix form is row, comma, column. And we're going to use that code to fix our problem children. So I've checked it by running the table function, and I have 2 typos. So let's get rid of those typos. But the issue is, to find these typos, you have to check for things by row. Okay, so I'm looking for the bad data row by row. And so you put that logical operator, which is what this thing is, in the row section. And I have in my notes here the way to do it that doesn't always work, and so I'll show you this way, and then I'll tell you why it doesn't work, and then I'll show you the other way that should work for you better. So I'm going to show you both. This first one will work sometimes, but not all the time. Okay. So we're going to check for typos by row, and we're looking and scanning each participant to find their bad score. So the logical operator goes in the row spot. So let me also do no typos here of absences. Okay. So that 35 is clearly incorrect or way out of range. So we're going to screen the no typos dataset. Okay. And we're going to look for no typos $grade. And we're looking for where it's greater than 34. Okay. And so this will show me, if I run that, the one row that has the grade that's larger than 34. However, if I set this entire row to NA, oops, sorry, let me hit escape here. If I do this, it actually wipes out the entire row. And so if I update my no typos dataset, and I had a grade, sorry, the NA goes to the bottom here, of 35, I see how it wiped out the entire row, so you don't want to do that. So this is bad, don't do that. So let me back up. So this is what I mean about fixing things. And now I can just run all of this again, and we're back to where we started. So I have my 35 again. So what do I want to do to fix that? So I don't want to fix every single row. I just want to fix that one column, given that this row is bad. So what you want to do is type in the column name in the column section. So this has to match this. And it's in quotes because it's a name of a column and not a number. So we want to do this. And that will give us one data point. So you see how we went from one row to one data point. And that's the important part. So now I can wipe it out by typing NA like this and run that. And now you'll see that the person with the bad grade got one NA. And so the whole row now is just at one spot. And so we could do that for absences as well. Now the problem with this particular piece of code is that if there are NAs in the data set, so let's say they're already missing values in that column, it doesn't like this. It says that the data is not subscriptable, which there's something about using the $ operator with where if it already has NAs, it won't let you use logicals and search for more NAs. Okay. So the other way to do this is very similar to the next thing we're going to go into, but it is to use the naming piece at the front. See if I can remember this. So I've pulled that particular column. So I've got one column of data now. I want to find where that column of data is, greater than 34. Oh, gracious. I've already wiped that particular, I've wiped that particular thing out. So actually, let's do absences. Let's spell that correctly. Okay, so let me show you what I'm doing here. Let me just back up for a second. So I got no typos of absences. Okay, and so if I run that, that is one column of data. Okay. And we can use that to our advantage. So I want to find where no typos of absences is greater than 34. Okay. And so you see how it pulls up that one data point. So this is what we're trying to get to. We're trying to find where we can get down to just one data point and not the whole row. And now let's try setting that to NA. Okay. So it looks like it worked. Let's try this table function again. And it seems to be gone. Now let's make sure it didn't wipe out the whole row. So I'm going to sort absences here. And it didn't. It wiped out that one spot. Okay. And so I actually think this little bit of code is actually a little easier because it doesn't require you to remember the row, comma, column thing. We're using square bracket operators here because those work on one column at a time as well. And we're looking for where in this data set this thing's greater than 34 and setting it to NA. So I actually think this is a little cleaner. It also does not throw up a grump at you if the column already has NAs in it. So this code will work just as well. Alright, so that's how you fix one column at a time. What if we have a bunch of columns that we want to fix with the same rules? So all of the RS columns here, 1 through 14, have the exact same rule. Nothing less than 1 and nothing greater than 7. So the range here is 1 to 7. So what I want to do is fix anything too small, so less than 1, and too large, which is greater than 7. Okay. And so if you write those rules out for yourself, I think this next part will be a little easier. So you got to figure out what it is you want to find that's bad. So since the resiliency columns all have the same rules, we're going to fix those all at the same time. So the first thing to do is figure out what columns you want to replace, and this time we're going to use numbers because that rule, using numbers allows us to have NAs. So I'm going to go back to Studio here. So first figure out the columns. So we're doing the no typos data set, but how can I figure out which columns I want? Okay. So I got to figure out, how do I know which ones? The ls, oh sorry, that's a different one. The names function allows you to see the names of the columns in order. The ls function puts them in alphabetical order. So if I do names of no typos, it gives them to me here in order. So if you have a data set with several hundred columns, this is the useful function for you. And I would just count. So number 10 here is RS5. So I could count over. So this is 1, because it's got the little 1 next to it. 2, 3, 4, 5, 6 is where I start, and 19 is where I end. So that's how I came up with the numbers 6 through 19. But since I'm not sure, I'm just going to check myself real quick. And I would run this, but it's going to give me a bunch of lines. So what we're going to do is use the head function. The head function just shows you the first 6 lines. And this is where I'm just checking to make sure I'm about to fix the right columns. So if you look down here, I'm 1 through 14, so these are the only columns I want to fix, and I can already tell I've got some NAs in here, but really right now we're dealing with typos. Right, so we found the columns we want. Now let's figure out the logical rule that I want. Okay. So we've already done that, greater than 7 or less than 1, and we're going to put those two things together. And so it's a little odd. This is a double bracket thing, but it's actually the same idea as this code, where I've got a single bracket, but because I'm dealing with a data set that I have to subset a bunch of columns at once and not just one column at a time, I have this piece of code. So this is the data set and those columns. Now I'm going to copy that again and say brackets give me everything greater than 7. Oops, greater than 7. And so the first set of brackets is give me all of these columns, very much like using this, but more than one column. The second bracket piece is give me that logical operator. So these two things will match. Okay, it's very similar to doing it this way. So I'm going to run that just to make sure it gives me the numbers I'm interested in. All right, so give me a bunch of NAs, because logical operators can't handle NAs. They come back as NAs. But also 18, 10, 10, 15, 15. So we're doing pretty good. It gave us the numbers we're interested in. So you might ask yourself, why don't you just delete the NAs and get it over with? Well, that's because the accuracy is before missing. So I'm going to handle these accuracy issues first. Now that we have this code that shows us the numbers we're interested in fixing, we can just set it to NA. And that will wipe out all the things greater than 7. But if you aren't sure, let's do a summary for no typos. And now I should have nothing larger than 7. And I didn't have any ones that were too small. So here are all my 7s. And that 11 is okay because it's part of grade. 7, 7, 7. And so that's how you can fix accuracy. Got excited. I'm going the wrong way, I think. For one row, one column versus lots of columns. So one at a time, you would do dataset name, $ column name, brackets, dataset name, $ column name, logical, okay, equals NA. For multiple columns at a time, you would do dataset numbers. Okay, and that might be like 1, 2, 8, 15, whatever. So you'd use the combine function, or C. And then the second set of brackets, no space here, we'll freak out. With dataset name, numbers, our logical operator, and then close that second bracket. Oops, sorry, equals NA. Okay. So that's one at a time and multiple at a time. Now, I'm going to put this next section under accuracy, mostly because you're going to check it multiple times, really, but it's also a good time to pick out those reverse coding issues. So I'm going to kind of show you how to check real quick the means and standard deviations. So the means you can get very easily from the summary function, but you can't get standard deviations. So if I'm looking at my means and standard deviations, this is a good time to check. Are they what I would expect them to be? Or do I have floor and ceiling effects? So I might know what I need to do in a little bit to deal with skew and kurtosis. Or if you're using reverse coded items and everything is like 5, 5, 5, 5, 2, you're like, oh, that item is either something's gone wrong or it's not been fixed. So it's useful to think about means and standard deviations multiple times, but we're going to start with checking it here. And so standard deviations indicate the spread. So very large spreads means you have a lot of error or some outliers or some more typos that you didn't notice. Or a very small spread, if you have no variance, that's also bad because you can't really run statistics with 0 variance because then you'd be dividing by 0 and that doesn't really work. And you got to remember that depends on the scale. So on a 1 to 7 scale, having a standard deviation of 1 or 2 points is pretty good. On a 1 to 100 scale, having a standard deviation of 1 to 2 points is really small. So what happened there? So the data will be very kurtotic. Okay. So we're going to use the apply function. If you've been watching my videos, I haven't used apply yet. So this is not tapply. Apply is very similar to tapply, but it calculates your function by row or by column. Whereas tapply calculates your function split on variables. So tapply is really great for levels and conditions. Apply is really an awesome function for column mean or row means. Okay, they're all functions, column means and row means, but apply is a little quicker, and it's one function instead of 2. So the way apply works is you stick in the dataset name. You literally type 1 or 2, not both of them together. Pick one. And then the function, so that's listed as fun. One is for rows, two is for columns. So if you remember the order of matrix, the matrix stuff, rows go first, two columns for second. Function can be mean, standard deviation, skew, kurtosis when we get there in the assumptions video. Length, so it could be a bunch of different ones. Histograms, you can make a bunch of histograms at once. And let's just try this and then we'll talk about why it doesn't work. So let me look at means and standard deviations. And so I'm just going to try this. So let's go apply, no typos. Let's do 2 for columns, that makes the most sense. And let's just do means. So mean. Okay. And so it gave me 19 warnings and a bunch of NAs. And so the first problem we have is, if you want to look at all the warnings, oh my goodness, look at all this stuff. Our argument is not numeric or logical. Okay. It's not terribly happy with us if you try to pass a factor variable through the apply with the mean. So anytime you try to take a mean of a variable that's factored, it's not terribly happy with you. Okay. And so what you want to do is exclude those columns. So almost throughout the rest of this, after you've screened the factor variables for typos, you're just going to keep dropping them because you don't want to get rid of them. You just don't want to use them in particular data screening points. So the first thing I'm going to do is just drop those 2 columns. And if I'm not sure which 2 columns they are, I can do the names function. Okay. And so it's 1 and 3 because gender and SES are factored. So how to do that? So I'm going to do my square brackets. I want all rows, so I'm going to leave the row spot blank to give me all rows. And then for the column spot, I want to get rid of 1 and 3. Well, the drop function is the minus sign, and then I'm going to keep 1 and 3. So I have dropped columns 1 and 3. If you aren't sure exactly what that does, try running it just a little piece by piece. Nope, I need that bracket. There we go. So that dropped sex and SES here. So I've got age. So all of these are contiguous variables now. So now we should be good, right? Let's see what happens now. Now it just gave me a bunch of NAs. So I didn't get the warnings. That's better. But now I have NAs. So what do I do now? And so we did this. And so now the real problem is all these NA values. So apply lets you pass other pieces of a function into its arguments by adding them on the end. They have to go on the end. It's dataset, comma, runner2, comma, function, and then comma, all the other things. So you can use this to run a bunch of things at once, but remember these have to go on the end. So I still don't understand why the default for this is not true. But na.rm, remember, is to remove na values. And so the default on that is false, so we have to set it. So let's copy this line. Okay, na.rm equals true here. Now it's dropped all of my nas, and so this should match the summary function. Okay. And so the mean for age on summary is 1505. And the mean for age here is 1505. Okay. And so it matches the summary function. The apply function, I feel like, just gives it to you in a much cleaner format that's easier to read, but that's up to you, whichever one you want to use. However, now I can throw in SD for standard deviation and get all the standard deviations really quickly too. So that's nice. And they look about right. They're all about 2 points. Which is not too surprising for a 1 to 7 scale. So I'm doing good. I don't have no variance, because no variance is bad. I have at least some variance. And my variance doesn't seem too crazy huge. And so that's how you deal with the NA problem using apply. Now remember, you might have to look up what this code is, because some of them it's na.rm, some like for cove and correlations, it's use pairwise complete.obs, pairwise.complete.obs. So it just kind of depends on which NA piece is programmed into that function. So all of that is how do I clean out typos and other accuracy issues with my data set. The next video is going to cover missing data.